Just talking about this today, yes. Give me a second, give me a second, give me a second. I brought some samples with me, and here we go. Yes, my name is Klemp. I'm a kind of dinosaurus in the area of 3D printing. Have led the research center in Paderborn, have done some production issues in Düsseldorf for voestalpine, and now I try to transform the production of bipolar plates, and I will explain later what is this, what we are doing here with 3D printing for it's a new application in order to be faster and to get a better performance, which is really the idea. So first I will come to the company itself. It moves on with this. Yes, here. I will tell you a little bit about the history of the company. This is vital if we compare it to additive manufacturing. So just buying a printer, just trying to get some parts, has no value if you don't have the complete value chain and the complete machinery there. Then I will tell you a little bit about fuel cell. I will just show you rough what we are doing. And the production of bipolar plates, which is the issue at the moment. And finally, I will tell you the challenges you have to cover if you want to produce bipolar plates by additive manufacturing. So, company and the history. We are old, so we are since 45, and we are producing at the end molds, parts. And so plastic molds for plastic, parts in plastic, in thermoplastics, in duroplastics, and in Duramus and thermoplastics and rubber. And you need this history. You need a factory which has all done through and went all through these processes. Just to see here, we have, as I said here, we are doing tool production, we are doing parts, and we're working for batteries and fuel cells. So, which are our products today? So we are dealing with automotive parts, we are dealing with healthcare parts, and finally, and here you can already see, we are dealing here with parts for fuel cells and electrolysers made out of additive manufacturing and assembled in order to let our customers build up a stack. So we have molds for rubber, we have molds for silicon, which is a kind of similarity. We produce molds for thermoplastics, and then we go for small series. And that is the combination with additive manufacturing. So in additive manufacturing, you have that small series or step-by-step series, and this is what you need. We try to bring this into a serial production, and you can see here as already injection molding for our parts, and it will be a part for our fuel cells. And we are doing some kinds of 3D printing, which is not that big stuff we are doing. We have presented last year a mold at the VDMA booth where we are producing parts out of an additive manufacturing being produced mold, where we are much faster. We are using bionic design and conformal cooling, and we were much faster, and it was comparable. So additive manufacturing is really a solution, but you have to know what you are doing. If you see, now we are leaving a little bit that part, and I want to emphasize, if you look here, how the growth is going on for fuel cells. So with fuel cells, I will explain later. Here you're getting electrical energy out of hydrogen. And you see the market is growing, and that is what we see. So having the standard production, we have to ramp up on another side. And that is our future. So fuel cells, energy, and so on. The next step is for electrolysers. With electrolysers, you take electrical energy, turn it into hydrogen. How does it work? You can see here, I will skip this, but that is the secret behind. You put in some fuel, the fuel comes out. Here you're dividing the electrodes against each other. That is what we need. Parts we need from our production in order to produce this. then we have air, and very important here, you get electricity out. So I'm driving a Toyota Mirai, which is working with this principle. So I put in some hydrogen, and I get in energy, which drives the car. You need many of those cells. So this here, the cell we have here, that's a 1 kilowatt stack. You need many of these elements. Oh, I skipped it too early, but you need many of these elements in order to get a complete stack. And if you have the stack, you get the energy out. So our idea is, how can we use additive manufacturing in order to become faster and to get a USP? So don't use additive manufacturing, just you want to use additive manufacturing, always use it with a USP. So here we have a stack, a 1 kilowatt stack. That is the energy we can produce easily, and that is what we have already produced. So here are our plates, which look like this. So this is a standard size, approximately A4, so 21 by 30, approximately. This is the size we are producing. So how do we do this? What can we do in producing these bipolar plates? We have different kinds of technologies. So we can do it by compression molding. So we take, our next slide will be powder we see. It will be compressed. It can be done to blank plates, which are later compressed. So first do it in a complete way, or do it the halfway and then the other way. We can do it mold to size, means we will have finished products. So it comes a little bit with the compression, but we can drill it, mill it as well, and that is interesting. We will go, or we hope to go into injection molding. Therefore, we will need special tools which can be produced by additive manufacturing. So if you see this, it's a pretty dirty job. We are talking about graphite. We are talking about dirty graphite. You look like your skin is not pale, and you will have dirty hands. And we are good in compounding. So this is what I said before. Having knowledge about injection molding, you know about the materials. We developed our own materials in order to get the right powder. Then one possibility is to get a foil, so to press it slightly, then to roll it. That will be a long way you can take it. And then you are stamping this under heat, and that is really the problem. It's really comparable to additive manufacturing, and I've done additive manufacturing since 1997. You need pressure, temperature, duration, and a lot of skills. That is what we have here, and that is what we are using in order to get to this point. If we go for injection molding, it's the same. So we have our compounding, so we can extrude our material. And the good thing of additive, if you're selling a part, you can tell them, okay, we have processed this with a PA12, but you will not deliver your parameters of the machine to your customer. It will be just the part. And so do we. We know the compound, we know the material, we know how to process, but we will deliver the plate. And we're just delivering the plate, not the process parameters. And at the end, you see, we are doing this with injection molding, and we get nearly ready-to-use plates, and we are testing them as well. So this is what you have to do, and that is a comparison to additive manufacturing. You have to test your materials, you have to test your final product, and you have to show, yes, it fits. And this is the real dirty job. So we have the compound, we put the compound as a powder into a mold, and we are rockling this. And I don't know how familiar you are with additive manufacturing, but if you look into the plastic machines of whomever who are processing PA12, you have a rockling system which is putting in a very constant way materials in a thickness. And this is our problem as well. So if you have an additive manufacturing machine where the rakel, where the sword is not even, or that rolling stuff with the DTM or now 3D Systems machine, if this is not working, you will have a shitty load of material. That is what we, and that is the aim of my talk, that is what we want to use. So we need the knowledge of additive manufacturing in order to get this. Having said this, so here you see we have someone who's very, very fine. And if you just do the rakeling in this way, it's a different way than that way. So if you put it this way, or that way, totally different story. And you have to get into the corners. It's the same stuff. Therefore, we designed a rakeling system which is in a schematic way, so I have to keep some secrets, which is done in this way. So this is a little bit comparing to using additive manufacturing machines for EOS, SLM, and so on and so on, so we know all those guys. Obviously, this is double. This is an interesting slide. Every slide is interesting, okay. But this slide is interesting as we build a cylinder in additive manufacturing, metal process in nickel. And we put in here a grid. This is a griddy structure. And this structure, I'm familiar with a few universities, and we made some tests with this. At the end, we cut it down, sliced with this. Having said this and showing this there up above, we need a high surface. As well, very interesting and very, very comparable to additive manufacturing. So in additive manufacturing, in metal, you try to get it as tight as possible. Surface as smooth as possible. And if you're using the wrong parameters, you will get a very rough surface. And if you're going for electrolysers, you will need a very high amount of surface, and that is what we have done. So go a little bit out of focus and get this. Having done this, we have to prepare these slides. We put in, now we are coming again to one of the first slides. We are very good in sealings as well. We put in some sealings. This is the part for electrolysers. And the big story is really we want to get electrolysers where we produce hydrogen out of electrical energy. And in fuel cells, we want to use the hydrogen in order to get electrical energy. We are losing, that's now more general, we are losing a lot of energy in between, so we have a 30% lose at every step. But at the end, you have more than nothing. So if that windmill is stopping and doing nothing, or it's producing hydrogen, you get more than you have. And this is our idea. So to produce hydrogen with this technology. And we have a guy it's not easy to put this together. We have a guy, in Germany you will know the guy Daniel Düsentrieb. It's an inventor out of Mickey Mouse, or wo kommt Daniel Düsentrieb her? So one of those. And he's an inventor, and we have such an inventor, and he's very, very funny guy, and he's doing this for us. So here we are in a very, very early stage. And that is what I want to tell you. We are here in an early stage comparable to additive manufacturing in the early 2000s. And I'm totally convinced here a lot of things will happen. What we have already done, we have produced nickel and titanium plates out of the additive manufacturing process. But if you see this here, this size, it's approximately this size. We need a dimensional accuracy down to 10 microns. And each powder has 30, 50 microns. Each laser has a beam of 50 microns. So here we have difficulties to use this directly out of additive manufacturing of the metal process. So sometimes we go with the know-how of injection molding into a MIM process, metal injection molding. So then suddenly it might be possible to get such a structure. But it's not that easy. If we summarize this, we are doing the compounding. So you have to know a lot of the material, how to process this. You have to know how to put it into your mold, compare it to additive manufacturing. That's vital. And I've seen the machine of DMG. They have done really a lot how to get the powder in line, not to moving into that machine. We have seen EOS and so on. They are all working on this. This is a real problem, and this is something we are doing real. Injection molding, mature technology, in combination, it's good. But here we're using more duromers, less thermoplastics. So as well, here's a problematic. What I forgot to mention is we have a 80% plastic and 20% graphite into a bipolar plate. This is the trick, and so this is how we process this. So, and if you that is the last slide I will show. You have to bring this together. If we go for powder beam machines and so on, this can be processed with additive manufacturing. If you afterwards slide it by EDM, for example, you have to cut it, and there are some more secrets than just getting the parameters a little bit wrong. A very interesting new technology is screen printing, which has not so much to do with the additive in itself. You're doing layer by layer through a screen, but here we have designed a material which can be processed by screen printing, and then you can get out these slides of bipolar plates. But, and this is a big but, the material has to fit, and the main aim of this bipolar plate is it has to have an electrical conductivity. This is difficult to bring in, and this is as well the problem with additive manufacturing. So if you have only one material, it's difficult to get a deviation in this way or that way. Or you have some holes in it or whatever. So that is one of the problems. The next problem is, as you have hydrogen, the hydrogen should not be allowed to go through. So bipolar, so we do electrodes on both sides. So we have to get a good permeability. Means we need a lot of plastic to get the bipolar plates tight, and we need a lot of graphite in order to get a good conductivity. This is our problem, and that is something we try to solve, and we are a little bit convinced that screen printing will be a solution, but screen printing on its own will not be the solution. So there will be maybe one, maybe two steps more. If we are going for stacks, so the stacks I showed has with a 1 kilowatt has just 96 bipolar plates or elements. That means we need a lot of plates being produced, processed in a very fast way. So additive manufacturing might not be the overall solution. It can be the first step solution. And with the screen printing, it might be one of the steps. Yeah. And we have to, if you see these holes, and as I said, we are talking about dimensional accuracy about a few microns. So customers of us talk about 5 microns accuracy. My hair has 100. So they want to be 20 times less than the thickness of a hair. And gray hair is a little bit thicker, so your hair will be a little bit more thinner. But we are talking about this, and this is a real problem. And these are the same problems we had with additive manufacturing right from the beginning. So I encourage you, think of new processes, think how we can solve this permeability, electrical conductivity, dimensional accuracy, and so on, and get the right material. With this, we will be able to produce hydrogen or to use hydrogen in a very efficient way. And here are I have to tell you, there are a few more secrets behind, which I am not allowed to tell, or which I'm not willing to tell, as I have to talk next year again. I say thank you for being here, listening to my talk. Hope it was a little bit interesting, and hope to see you next year again when I have a little bit more results as we are moving forward. And hydrogen, that is our mission. That is what we see. Step out of the old processes, moving into the future. That is what we want to do. Thanks a lot for your attention.